All right, here's Mac, retired physicist, expert, longtime activist on green energy and the environment. Take it away, Mac.
Okay, so thank you, Doug, and thank you special to Jim and to the members of the Senior Climate Action Group. So our objective tonight, if this thing will let me do that, three things. The first, to try to explain how heat pumps work. Second, why they're more efficient than any other kind of system. And third, I'll show you some pictures of what these things actually look like. So a heat pump is a device that uses a refrigerant to move heat from one location at a given temperature and another location at a different temperature. So that means we could extract heat from a cold place and dump it to another place to provide heat. So, so why are heat pumps so important? So first is no on-site use of fossil fuels, and that is the enabling technology for electrification. So without heat pumps, we'd have a hard time for justifying electrification. Second, it provides both heating and cooling, and it's more efficient than any other kind of system. So you already know heat pumps, like your refrigerator is a heat pump, your winter air conditioner heat pump, your automobile, and so on. And I added chillers, even though that you're probably not familiar with chillers, was my favorite form of heat pump. And I'll just say a little bit about it as a sort of add-on a little later. So heat pumps operate in a vapor compression refrigeration cycle. This cycle was described by a young Frenchman in his 20s in 1824, almost 200 years ago. So in his honor, this cycle is also sometimes called the Carnot cycle. So this cycle is based on three physical principles. The first and the most important one is that heat travels only from hot to cold. Thermal energy moves only from hot to cold, regardless of how small that difference. The second is that the temperature of a gas decreases when the pressure or increases, that is, when the pressure increases, and decreases when the pressure decreases. So heat pump has four major components: a compressor, or which increases and decreases the pressure, an evaporator coil, a condensing coil, and an expansion valve. And we can't forget the refrigerant also, a major thing. So a refrigerant is a fluid that can easily boil, that is, evaporate from a liquid into a vapor, and then condense from a vapor back to a liquid. This is why this is called a cycle. So heat pump components, we said, have four parts: condenser, an evaporator, expansion valve, and a compressor. So this line represents a tube with refrigerant in it. So say a refrigerator is as a heat pump might have a pound of refrigerant in it or so. A large heat pump might have 7 or 8 pounds of refrigerant. So the purpose of this expansion valve was to provide a sort of demarcation between a high pressure side and a low pressure side. So let's actually look at a heat pump in a heating mode. So again, we have to follow this basic principle that heat travels only from hot to cold. So if our purpose is to extract heat from the outside air, we live in a sea of thermal energy. And so we can extract that energy provided that we create the conditions to do that. So if we want to extract heat from the outside, regardless of what the temperature is, and dump it to the inside, we have to make this evaporator coil colder than the outside. So you pick a temperature, regardless of what it is, we'll extract heat if we make this colder. So we extract this vapor that's now picked up this thermal energy. We compress it, and by increasing the pressure, we make that vapor hotter. It turns to a liquid. If the condition we creating is this is hotter than this side, so if the temperature here was 65 and we want to get it to 70, so this has to be maybe whatever 80 whatever degrees, or it could be just a few degrees above this. So this becomes a liquid, and we go through the expansion valve and we repeat this cycle over and over. So if we want to, this is the heating mode, we can also cool, reverse the cycle. If the objective is to extract heat from the inside and dump it to the outside, we have to make this set of coils colder than this one. So again, we repeat this cycle, hot to cold. And again, it's not as often a question, well, how, say for example, if this is a hot summer day, can this work? So say if this is a mile, 80 degrees, this has to be 90 or more. If this is 110, this is maybe 120 or whatever. So the compressor works harder if the higher this gets. Okay, so an important point is the name of the evaporator and the condenser is based on the function, not the location. So let's back up a bit. No, I want to go the other way. Okay, so here you notice that we're calling this the evaporator. Here we're calling it the condenser because we're in the heating mode. So it's the same physical device, its function based on the direction. You notice also that the direction of the flow is different. In reality, we wouldn't be physically reversing the direction of the compressor. We use a simple plumbing system called a reversing valve. Okay. So what about fans? Yeah, so again, this is the basic fundamental system, but in a real system, you have a fan here and there to move the air. And the other question was, well, what can we do about efficiency? We're going to talk about why heat pump is more efficient, but in terms of what could we do to make the system as it is? What determines the efficiency of a simple system like this? The compressor is the limiting factor. Okay, so we provide electricity to operate this compressor, but there are a couple of things we can do. Say another reality of a real system is you'd have a thermostat. The thermostat would tell the system, the compressor, turn on. So it would turn on, run full speed, and then the thermostat says turn off, the compressor turns off. And so you go up and down, up and down. A better system, more efficient system would be if this compressor could just respond to the load and not overshoot it. So to do that, we use what's called an inverter. So we have inverter-driven compressor, and what it essentially does is exactly matches the amount of refrigerant that goes through that expansion valve to the demand. So that's called using a inverter-driven compressor enables us to provide to vary the amount of refrigerant flow. And so any system in which you can change the speed of the compressor to match the need of the amount of refrigerant you need. Is called a variable refrigerant flow, or VRF. So that's the new buzzword. And it's new and popular in the United States, but it actually was started in Japan almost 30 years ago. So three major types of heat pumps. And going back a bit again, as you recall, we're talking about extracting heat from the outside air, from this sea of energy. So we would call these pumps air source heat pumps, because this is the source of we're getting this thermal energy from. So we could also, if we were using water, we would call it a water source heat pump. If we were extracting the heat from the ground, we call it a ground source heat pump. Also call it geothermal system. Okay, so let's say look at let's look at a ground source heat pump. So we still have the basic components, condenser. Let's say we put the evaporator underground. So here's the evaporator. And so we would be taking advantage of the sort of constant temperature of the ground. We'd have a refrigerant lines going in. But this is a terrible idea. That there was a company in Florida about 20 years ago that actually made a system like this. It's very efficient because you have copper tubing that conducts heat well. But the problem is copper deteriorates, and you got a lot of expensive refrigerant here. If you spring a leak, you contaminate the whatever. So this is a bad idea, but it works well. So an alternative would be to instead keep the system together. Say in the heating mode, we got this evaporator here. We put it, say, in a tank of water, then pump the water through tubes that we put in the ground. In reality, you'd have a heat exchanger, but this is the concept. So, so the way you would do this, you could say nobody would do a system like this. You'd make trenches, but this is the idea. Or the preferred way is to do this. You put these tubes, drill holes, bore holes, put these in. So notice this is a closed system. These are not wells. There's no connection. Here is a representation of an aquifer, water. So you'd never have an open system where you're actually drawing water from the aquifer. You can do that, and it works great, but in a state like Illinois, that is strictly forbidden to have an open system. So, at a water source heat pump, you would take the evaporator, put it in the water. That's actually done. So instead of doing that, you could have use a cooling tower to have a water source heat pump. Actually, the Walgreens on Madison and Oak Park Avenue has a hybrid system. They have a geothermal system and a cooling tower. So they have it's a hybrid. So we've been talking about heating air. So what if you needed to heat or cool water? So what you would do, so the systems we've been using, we'd call it air source to air heat pumps, but you could have an air source to water heat pump, where inside, instead of just having a fan blowing over this hot coil to heat the air, you could instead heat the water and say connect this to a radiator or something. Okay, so that would be called an air source to water heat pump. The concept still applies, removing heat from hot coal. Okay, so the size of heat pumps, I mentioned before that, say, these coils, or say for a refrigerator, or say a medium-sized heat pump, this would be, these tubes would be maybe the size of a pencil or a drinking straw. But this system is so versatile that it could be any size. Again, my favorite type of heat pump is a chiller, where you got a huge tank here. So instead of having a tiny pencil-sized tube, you have tanks that are size of a, you could crawl through it. So still these tanks, I mentioned that say a heat pump might have, a refrigerator might have a pound of refrigerant. You could have these tanks that would have hundreds of pounds of refrigerant. Again, this is the condenser, this is the evaporator. You still got the pump and the expansion valve as before. So the first heat pump was built in 1922. So this is the 100-year anniversary of the chiller. It was by Willis Carrier. He started the Carrier Company. Interesting side fact is that in 1922, a Model T Ford was $250. A residential refrigerator was $750. I got a little note here that in rural Louisiana in the 1940s, nobody had a refrigerator. But my Uncle Joe was converting what is it? Ice boxes to refrigerators. So he had an evaporator the size of a plate, and he had the condenser and compressor outside. So he was kind of ahead of his time. So this is a modern a chiller. The library actually has a chiller similar to this. So this is the evaporator as the condenser. The largest heat pump in the world, I think, is in it somewheres in the Emirates. I think you can say you can drive a car to it. So heat pumps are more efficient than any other gas or boiler. So I know you believe that. I haven't really said anything about that yet, but this is what it's all about. So now I want to try to show you why a heat pump is more efficient than any other kind of heating or cooling system. Okay, so what do we mean by efficiency? By efficiency, we mean, by definition, it's the amount of energy we get out divided by the amount of energy we put in, what we pay for. So when we talk about efficiency, we have to consider the conservation of energy, which says the first law of dynamics tells us that in any thermal system, the amount of energy you get out has to be equal to what you put in. So you can't lose any. What you put in is what you get out. Okay, so we look at let's look at the efficiency of a natural gas furnace. So let's say this is the gas furnace. We burn natural gas. This is what energy we're putting in. This is what we pay for. We get two things out. We get useful heat out, and we also get some energy out from the combustion products and water vapor and whatnot. This will go up the chimney or up a PVC pipe. You can see steam coming out. So applying that first law of thermodynamics that says what we put in has to be equal to what we get out. So this is what we put in. What we get out is this plus this. But this is a useful energy. This is all that is useful to us. So this is then
from lack of insulation.
Oh, or leaks and all sorts of
Leaks
stuff.
and things like that.
Somebody mute.
so this then is equal to what we put here minus this. So that makes sense?
Mhm.
See what we put in these two are what we get out, but this is equal to this minus this. Okay, so what that means is the efficiency of a natural gas furnace, the useful energy out.
And it sits right there.
Hey,
you-
Wilkies, can you put yourselves on mute?
Say, Jim, could you? So this is the useful energy out divided by what we put in. This is what we pay for. But this useful part out is what we put in minus what we lost. So this number is less than this number. This number is smaller than this. So that means that the efficiency of a natural gas furnace or any kind of fossil fuel system has to be less than 1. In the say 80s, a gas furnace, this number was like 0.8, 80% efficiency. Today, gas furnaces and or in a 90 some, as much as 98%, 0.98, 98% efficient, but they'll never get, it's impossible to get to 1. They'll always be less than 1. Okay, so let's compare that to efficiency of a heat pump in a heating mode. Again, we pay for the electricity to operate the compressor. So this is the amount of energy we're putting in the system. So the purpose of putting this energy in is to create the condition so that we can absorb energy from the sea of air or water or ground. So we have 2 inputs, what we're paying for, what we absorb. We get 1 output. That's the useful energy that's released into the indoors. So again, following that first law of dynamics, of thermodynamics, that tells us the input has to be equal to the output. So this plus this has to equal that. What we release indoors is what we paid for here, plus what we absorbed from the outside. So when we looked at that ratio, and when we talk about efficiency of heat pump, the preferred term is the coefficient of performance rather than efficiency, because we use a number. We don't multiply it by 100 to get what the efficiency is. So we talk about the coefficient of performance. So the coefficient of performance of our heat pump is, again, what we release to the indoors divided by what we pay for to operate the compressor. But the energy we get indoors, back up again, look at that, is equal to sum of these 2 things. So it means that this, what we get out is what we paid for the compressor plus what we absorbed. So this number is larger than this one. So this means that the coefficient of performance of a heat pump is always greater than 1. So this is what it's all about. So the coefficient of performance of a gas furnace is always some number less than 1. That will never change. The coefficient of performance of a heat pump is always greater than 1. If it's not greater than 1, it's not a heat pump. So for air source heat pumps, that coefficient of performance is something between 2 and 3. So that's meaning an air source heat pump. If we let a gas furnace let's say round this off to 1, is 2 to 3 times more efficient than a gas furnace. For an air source to water heat pump, that is, you're using air as the source, but you're using it to heat water. It actually has a coefficient of performance of 3 to 4. The ground source heat pump has a coefficient of performance of 3 to 5. These numbers will change, will increase as the technology improves. This number will never change. Okay, so that's what it's all about. And so again, this is the enabling technology for electrification. So what about costs? So because a heat pump has a coefficient of performance greater than 1, and it could be anywhere from 2 to much as 5, we use less energy than any gas-fired system. But people rightly point out that, say, right now in Illinois, the cost of electricity is higher than that of gas. So for example, if say the cost of electricity was twice that of gas, then if we have a coefficient of performance of 2, then we're using half the amount of energy. So even though the cost is double, it's a wash because we're using half the amount of energy. If say the cost of electricity was 3 times more, and we got a heat pump that's the coefficient of performance of 3, it's still a wash. But if we're using a heat pump with a coefficient of 2 and electricity 3 times more, then it's costing us more than it would if we used gas. But we can't forget why we're doing all of this. We're doing this because we have a crisis with the use of fossil fuel. So the heat pump, we use no fossil fuel. So even if it costs more, it's worth doing. So, but again, a valid argument, well, yeah, it's, you're using less energy, but the electricity we're using isn't all from renewable sources. We're still using 10 to 15%, only 10 to 15% of is from renewable sources and the rest from gas. But we're still using less energy. So we use, even though we use our electricity isn't 100% renewable, we're still using less. So over time, that will improve, but we use less greenhouse gases. But natural gas will never decrease in its greenhouse gas emissions. Okay, so in summary, heat pumps provide both heating and cooling. It's more efficient than any gas fossil fuel system. We use less energy, so it costs less to operate, maybe, depending on what that ratio is from cost of gas to electricity. And we have no on-site use of fossil fuel. So it reduces our emissions, even if our electricity is not fully all renewable energy. So again, heat pumps are the enabling technology for electrification.
Wow.
So it's a simple machine that could save the world. And so I have some pictures. And so as you've seen so far, heat pumps are 2 parts. I had that line I didn't point out what that was, that red line down the center. So 2 parts. There's the indoor part, we call it indoor unit, and an outside part. So I'll first talk about some pictures of the outdoor part of the heat pump system. So this is a combination of both. So this, again, heat pumps have those 4 components. This is a system, you mount this system on the wall. A coil is in here. This part is outside. This part has a coil and a compressor and an expansion valve. This is a tube that you connect the 2 together. So this is a really small system. It's only 100 kilowatt. The toaster you have is more than, I'm sure is more than this. The typical toaster is about 1200 watts. So in this system, this particular one, I forget, made by Seville, it's 120 volts. So if you want to just try this, say for that room that is never quite, either too hot in the summer or too cold in the winter, to give it a try or whatever, put in the basement or whatever. So for this still system costs less than $1,000. Okay, so this is called a split system because this part is separated from this. This part is outside, this part is inside, and it's mini, of course, because it's small. So this gives you an idea of the size of that. We put that in a shopping cart. We buy one from Home Depot. This is, again, this part is the outside part that has the coil and the compressor and the expansion valve. This is the inside part that has the coil. Okay, so the outside heat pump, I just showed this to show it is mounted on the wall because you wouldn't want it to be covered in snow if you're gonna use it in the heating mode. Heat pump, outside heat pump. You can have more than one. You can have zones if you want. You could operate, say this for operating those mini splits that I showed you. Could be in the downstairs, this upstairs, whatever. You could have many of them. This is, you have a system that operates many different indoor units. This is a heat pump that I noticed. It's on Madison and Risland. It's behind the new bank. So this is a heat pump system, I would guess, is 5 to 6 tons, serves the heating and cooling for this building. Here it is here. Took a picture from across the street. It's the bank. Okay, so here's a outside unit for a large building. These are outdoor units. This kind of system could operate up to 50 indoor units, but this would be used only for a large building. So here's an example of what we call an air handler. So in this box, you would have, again, we still have those 4 components. You have a coil here. This is inside. You have the coil here, and you have a duct system. So if you already have for example, if you had, say, a gas-fired furnace and you want to switch to a heat pump and you already have a duct system, you take out your gas-fired furnace, put in this air handler. The air handler has a coil with the refrigerant in it and has a fan. So watch this set of coils. This is the outside unit, and here's this set of coil. Go back. So again, you have this coil. Could be, depending on which mode you're in, this is the condenser. In the heating mode would be the evaporator in the cooling mode. So you have this refrigerant driving the condensing unit here. And you have this outside unit. So this is an example of a ground source heat pump. I'm sitting up just a few feet away from it. This is an 11-year-old system. Here I had a gas-fired furnace, and so 11 years ago I removed the gas-fired furnace and put this in its place. It's about the same size, so you can see the duct here. This is my logbook, which I've been keeping for about 11 years. So what's in this system? There's again a coil. The coil is this wide. This is a filter. So and in the bottom part here, so this is a self-contained system. Everything is in this box. The main coil is here. Under here is the compressor, the expansion valve, and the other part of the other coil that's in the form of a heat exchanger. So in terms, it might be just of interest that in 11 years, I had three repairs. The first one was 3 years ago that this coil failed. And I was told it was due to a manufacturing problem that they had with the coating. So they expected it to fail. They were actually doing a recall. So so it was replaced. It cost $1,000, but it was within warranty. So I only paid for the installation cost. A couple months later, I came in and found water on the floor. It turned out there's a drip pan here. The drip pan had a crack in it, but I was able to fix it with some aquarium cement. About a year ago, the other failure was the system wouldn't start, and it was a $20 starting capacitor. So it's not bad for 11 years. The loop field is outside. This guy said he would keep an eye on it. So yeah, I want to go the other way. So again, those were the outdoor parts of the system. I will take a look at the indoor parts of the. So this is that example of that mini split that you saw. The mini split. This is a mini split that's mounted in the ceiling instead of the wall. And these are called high wall mini splits because they're mounted high wall, makes sense. This is again a ceiling mounted system. This is intended for retrofit because you could put this in the ceiling, but it would fit between the ceiling joists. So, but what if you had a high temperature boiler, say with a cast iron base motor radiator, hydronic system? What could you do? What are your options? So you could, instead of using an air to air heat pump, which all the ones we talked about so far, this is what they are. You could use an air source to water heat pump. So what you do is would be the air to water heat pump. You would put one coil in this tank, bring it up to the temperature you want, and then use these tubings to connect that to say the radiators. Use these pumps to pump these through the radiators. So something like this, you know, the heat pump, a buffer tank, and you provide the different radiators. So the problem is, and I mentioned at the very beginning, we could get any temperature you wanted. I could go all the way back to the beginning, but I think the point is that if you're in a heating mode and you wanted to have I'm lost for word, the hot part of the condenser at say whatever temperature you wanted. By design, you could do that, but the question, for example, the typical condensing unit, if you want inside temperature to be 70 degrees, the typical condensing temperature is the order of the 90 to 100 degrees or so. But if you wanted to get a higher temperature, you could. But the question, why would you want to do that? So heat pumps today, are the maximum temperature based on the choice of refrigerant and compressor are in a range of 110, 120 degrees. So the traditional, where we are. So the traditional radiator work doesn't have enough surface area for that to work. So for example, this low temperature flat panel radiator has a surface area of 3 or 4 times greater than this one. So one wanted to switch from a conventional hydronic system where you have a high temperature boiler with conventional radiators. That one option would be to switch to air to water heat pump and use plate radiators. So it can be pretty fancy, but that's in a heating mode. But you have a heat pump that can provide both heating and cooling. So why not take advantage of it? So you could provide cold water to these radiators, but as you know, there's moisture in the air. So after a while, this radiator will get red, drip water on your floor. So you don't want to do that. So what you'd have to do is, instead of using radiators, unless you're not interested in air conditioning, that would be a perfect solution. But if you want to do cooling also, you have to switch to what is called a fan coil unit. So this would be, you have the coil here, but you'd also have a fan behind it. So they would look something like that. They would get pretty fancy, it'd be recessed. So like so. So you could have, if you had a hydronic system, you could switch, you'd have to switch to a air to water heat pump and use fan coil units. Okay, like so. Okay, an alternative that people don't talk about, you would also switch to what's called a high velocity air handler. So instead of having to move all of your radiators and replace them with the air handlers, you could switch to a high velocity air handler, drive this with an air to water heat pump, and use very small tubing. Say these are 2.5 inches diameter. You may have seen some of these, and you have these things in the floor or the ceiling. So the air comes out at a high velocity, but it's very quiet. And the way it's designed, that it washes off the wall, and you get perfect mixing. And so it's a really pretty efficient system. So that's something that one might consider. So I didn't mention that there's going to be a test. So the test is, if you had a window air conditioner, it's installed backwards, could it be used as a heater? Absolutely, yes.
Yes.
Actually, in every heat pump system, one side is going to be cooling and the other side is going to be hot. So if you put your hand behind on the outside of a window air conditioner, you know it's hot. Put your hand behind a refrigerator, you know it's hot. So there's a company that actually was making air conditioning. So all you had to do was add a reversing valve, and you got a swifter switch, and you heat the inside. It's not a very efficient system, but it can be done. So the other question is the window air conditioning, there's a split system. No, it's not, because you got everything is in one box compared to heat pumps, some heat pump system where for example, the high wall units, where that unit is outside, but the compressor and the reversing valve is outside. So a window air conditioner is not a good system. So this is, let's see, what time are we doing? We're not, so we're, let's see, so we're 40 minutes, huh? So I added this slide just an hour ago, and I call it risky because I suspect I'll get a lot of comments about this. So the questions, I know there's been a lot of questions about what are the people who have hydronic system gonna do? If they want to convert to a heat pump system, but they have a boiler, it has say 180 degree water, and they're using conventional radiators. So I listed a couple possible options. And again, nobody's gonna throw eggs at me. So, and this is just kind of for fun. So if you want to, I'd love to talk about it, later or something. So option one, the simplest one, say you want to do heating only. So you'd use an air source to water heat pump, replace all your radiators with panel radiators, the high efficiency panel radiators. but that's not, but you paid for a heat pump that can provide both, so why do that? So option B would be, again, you'd use an air to water heat pump. You'd replace the existing radiator with either high wall or low wall fan core units. Okay, so that's another option. Another option would be to use an air source to water heat pump or a ground source heat pump, and you'd install air handlers. Say if you have an attic that you're not physically using, you know, as a living space, you could put an air handler in the attic and then use short ducts to different rooms. You provide registers in the ceiling, and so you could also, that would be the simplest way, say for the second floor. You would also provide mini splits, say in a basement between the joists, and provide holes in the floor, whatever, to provide heating and cooling. That would be one option. Another option would be to use an air source to water. Let's see, air source to water. I meant to have or here, I got of. Yeah, I said I just did this an hour ago. Or an air source heat pump. And you didn't, so what you would do is just abandon the radiators, and you'd have could use one of those high velocity air handlers using the tiny tube. So training, and I had made a point not to say be an advocate for any particular brand or whatever, but these two companies are kind of special. This Enertech, they have a policy, so they specialize in air to water heat pumps for retrofits. So they have a condition that they will sell you their system to a contractor only if they take their training course. So I've taken, you have 10 videos, I've done 5 of them, and you have to pass the exam. So the other company, Arctic, takes a different approach. They say they will sell you their system only if you provide them with a copy of the manual J load calculation. Okay, so that's all I got. Any questions?
Yes, I got a ton of questions, but it looks like Jim's got his hand up first.
Okay.
Well, Susan, you can go. That's fine.
No, go ahead. I was just,
Well, I just wanted to thank Mac, first of all, and I really appreciate this. This is very, very informative, and I wish everyone in the village could see this, and I hope they do. And I also want to say the thought that about your uncle, the story about your uncle is funny, because the thought, the apple falling far from the tree or not falling far from the tree, kind of rings true. But I wanted to say, do these heat pumps generate excess energy? Is that something where they can be sold back to the system? Is that the type of thing? And who sells them? Where do you, like, is there a place where do you go to buy a heat pump? Where would you go?
Yeah, I don't know. What do you guys see? I don't know why I'm not. So
Hey,
am
Dad, I think you want to stop sharing your screen. Dad, I think you want to stop sharing your screen.
Okay. Stop sharing. Okay. Okay. Good. Okay. Yeah. So your question is, where do you buy them?
Yes.
So yeah, I think we're developing a list. I think the best thing is to start with is to get somebody to do a heat load calculation, and then depending on what kind of system you currently have, there are lots of sources out there. You just got, so the people that I recommend, I talk to all of them first. So that's something we can do, is develop a list of people who actually, so for example, in Oak Park, there are several dealers Uh,
And
So-
OPCAN and Mac OPCAN has put together a list. There is a
Yeah,
Google
yeah.
Doc
yeah, okay.
that I can share to interested
Yeah.
people.
But
who-
Jim, what was the other part? I kind of got distracted.
No problem. Do they generate excess energy that you, is this the type of thing where like you can sell back the excess? Is it generate excess? Because I
no,
know the efficiency,
No, this is not a,
it just, sorry,
no,
go ahead.
yeah, no, this is not, no, you generate no, there's, no, you generate, this is not generate energy at all. This is a system to extract energy and use it inside of it. So this is not, maybe you're thinking of geothermal or whatever. So that's a confusion that the industry has fought for years. They hate the term geothermal. I should have left the thing up so I could go back and, well, I guess I could still share my screen again. But the geothermal we're talking about is just having because the earth, say the first 100 feet or so, few hundred feet, maybe 500 feet or so is at a fairly constant temperature. So we're just taking advantage of that. But the geothermal with a big G, where you actually get thermal energy, is thousands of feet underground. So those are two different things. So you don't produce energy.
Ground source heat pump is, okay.
Thank you. Thank you very much.
So Mac, I had a couple questions. One is, well, sticking to that ground source.
Mhm.
So is there an issue that if everybody had ground source in a dense neighborhood, would
Mhm.
there be an issue with the ground being heated up? Like
Uh,
during when it was being used for cooling?
No, not if things were sized right. There are, let's see, 20 years ago, the Army in Louisiana created a community ground source heat pump system. So the short answer is no, if it's done right. No.
Yeah, okay.
For
Yeah, I'm told,
example, you could do much deeper boreholes, say down to 1,000 feet or so, like at the Statue of Liberty visitor center. They got 1,000-foot deep geothermal system.
wow.
Yeah.
Wow.
Yeah.
So yeah, I'm totally nerding out on this. I love it. Thank you so much for this talk. It's much clearer now. But I'm having trouble visualizing. So this split one where you have, you put something in your wall, is it blowing out hot air? So is it like a dry forced air heat?
No, yeah. So say the mini split that you
Yeah.
buy on the wall.
Yeah.
Okay, so it has three things. It has the coil and it has a fan, but that fan, how can I put it? Everybody comments on how quiet those systems are. They have fans that use the same technology used in your laptop. So those fans are tiny.
Oh,
but
wow.
so the air is distributed well. You won't feel it, you won't hear it. But it
So-
does have a, not so people are not, it does have a tiny drip pan. So I don't know if it would make sense that Linda, are you still there? My
Yeah,
daughter-
I'm here, Dad.
So if I went back, if I shared, I could go back.
Yeah, have it open ready on that slide that you want.
No.
So it's not, because I think I stayed in an Airbnb once that had something up near the ceiling that was an air
Yeah.
conditioner. and
So
it was-
that was a high wall mini.
No, but it was loud and windy and it was,
That was a bad system. There was something wrong with it.
I think it was just an air conditioner. I think it was just a wall unit.
Oh, yeah. There are other things you see in some motels and whatnot.
mhm.
Those are fan coil units, but they're not based on heat pumps. Yeah, those things can be terrible.
Yeah, like a hotel. Yeah, I think that's what I'm thinking.
Yeah.
Yeah, this is so so interesting. Okay, I don't think I have any more. Any more questions?
There's a question in the chat, Doug.
I didn't know to look.
Yeah. Jim,
So
Jim,
yeah, I think,
would you?
I think Jim Babcock had asked a question about how power panels that you need if you need something very large. So I actually called some electricians to get an idea what cost was. So I mentioned in that first little heat pump I showed you that was only a 1,000 watts and it was 120 volts. So you need, so there's, if you have an air conditioner already, you already have a 220 to 240 volt system. So you don't need any upgrade. So the systems do need 240 volts and maybe up to maybe 40, 50 volts, but you don't need any super whatever. So I called some electricians in the Oak Park here to see what that would cost. So the range I got was if you have a 100 amp system and you want to go to a 200 amp system, the price would be between $2,000 and $4,000.
Okay, don't forget, Jim Johnson has a.
Yeah. Here's the question he sent. Historically, heat pumps could only provide adequate heat for buildings with outdoor temperatures of 30 degrees Fahrenheit or higher. What improvements have been made to heat pumps to make them capable of providing heat in lower temperatures than that?
Yeah, so as I pointed out in the very beginning, it's a matter of design. Whatever you want, a heat pump could do it. Is based on what refrigerant you use, what compressor you use. So the heat pumps in the past were designed for use in moderate temperatures. So that the improvement, they're aiming at a different market. So the difference is improvements to make it economically profitable. You have compressors that are much better, and you're using different refrigerants. So the Department of Energy has a challenge out, a 2-year challenge for companies to develop 2 categories of heat pumps, -5 degrees, and I think the other is -15. So they want it to be, and they specified what the price range should be. Again, there are companies out there who would build a heat pump for any temperature, whatever you want it, but you'd have to pay for it. So it's like saying you want to have a Volkswagen Beetle that you want to go 300 miles an hour. You can do that if you want to, somebody to pay for it. But you say, why would you want to do that? So I guess the short answer is the improvements have been made in primarily in compressors and a selection of refrigerants. Yeah. Anything else? Yeah, Jim.
Yeah, Mac, your system is basically forced air, it seems like, and through that air handler, and you've got a unit you said is ground source heat. Could it also be just air source heat, but then it would just be less efficient, or
that's a good point. So I have a ground source heat pump system with a ducted system. So this is not, that system you saw is the whole thing. So I'm using the compressor and everything is all inside. So I'm not using an air to air or air to water heat pump, whatever. I have a non-split system that I'm just using the ground loop as my source. I don't know, does that make sense?
Yeah, yeah. So the heat's coming from the ground or the cooling and going into the house through tubes and into that air handler and the converter and everything. And then there's some kind of fan, or the air handler then pushes that hotter or colder air through the original ducts and then out in through the original ducts that are in the house. You didn't have, or theoretically, you wouldn't have to replace any of that ductwork that's there if someone has a gas forced air system now.
Yeah, we just replace, you could replace it with a geothermal system, or as I showed, as a with an air handler system. Yeah.
Okay.
So I don't know if I really answered your question. So there's a difference. I showed a case where you had a air source heat pump driving a air handler. So you had an inside coil that had a fan, that you had an existing gas-fired furnace that had a duct system. You replaced it with a air-to-air heat pump that you have outside, and you have the coil. You have the refrigerant going to the inside coil, and you have a fan. That's called an air handler. The system I have is not like that at all. It has my system. I don't have an outside coil. I have an inside coil. So I have both the condensing unit and the evaporator are both in that same box. The difference is that, say, the heat is that the inside coil is a heat exchanger. You know, because what it is about the size of a 5-gallon bucket, but it has, say, I forget how many, over 100 feet of coil. It has a coaxial coil in which the refrigerant is in the inside and the water flows to the outside. So I didn't show you in my system that I couldn't show you where the outside loop is connected to the bottom. So does that make sense? They're really two different systems. You have with an air-to-air heat pump system with a fan coil. You have the heat pump with the compressor and the coil outside. And then you have an inside coil. With the system I have with a ground source heat pump, I have both coils inside. And instead of having one coil exposed to the air, I have a set of coils with water bringing that to the inside coil.
Yeah.
That makes sense?
I think so. I think for me, and maybe for most people, it's going to take a few times going around this to have it sink in, and to maybe talk to people about our specific situations. I think the contractor list is a great idea. You know, if we can have somebody come out and take a look and say, here's what we recommend. I was going to ask also for the organizers if a copy of that PowerPoint maybe could be sent to, you know, everybody that signed up for this.
Yeah. So I have a question. I took the pictures and all of that, and I got lots more pictures and everything. Would it help if there was some place that you had actual heat pumps? There were different varieties, say in a mock-up setting or something that people could actually see. You understand the question?
The pictures were really useful themselves as pictures.
Pardon?
Just seeing it install. I thought the pictures were really helpful as is.
Mhm.
Seeing it installed, I think demystifies it a little bit. And what am I signing up for in my house?
Mhm. So you're saying you think that would help?
Right. I don't think that I would need something more, but I thought the pictures were really good, but curious what other people thought.
Okay, that's good then.
I would see maybe including a module on heat pumps as part of what I believe the Oak Park Climate Plan requires, which is an education center
Mhm.
on climate issues. So you would have a corner of that, and maybe you would have an actual physical heat pump there that people could put their hands on, and some interpretive signage similar to your slides.
Mhm.
Yeah, I think adding on to what Ken said, the thing is, there's a time lag. People have to know that these things exist. I would suppose that most people in Oak Park don't even know what the word heat pump means. And somehow that word has to get out. I think it was the same thing with solar panels. They were around, but nobody quite knew about it, if you care. But I don't know how we do that or how it's going to be done, but maybe I'm wrong, but I just think that most people in Oak Park don't even know the word, what it means.
So I heard of, I forget what city, they have a system where that, let's say you want to you have a gas-fired furnace and you want to replace it. You never heard a heat pump, and you call up installer and said, I need a replacement, or when can you do it? The guy comes over. So that person is required to tell you that, do you know about heat pumps? And I'll tell you about it. And the village has a program that will help you with the cost or whatever. But the bottom line is that the installers are required, before they install a gas or fossil fuel system, to inform the customer that these systems exist and they could be provided with some rebates. So, and that is true. There are rebates and tax credits and all kinds of things for these systems. So I don't know. So that's something that I guess the village is working on, maybe. Anybody know?
So what I've heard about that through just being a member of OP Climate Action Network is that there's a person that works for the village somewhere, whose name I think is Marcella, that is supposed to be hiring someone that will help to get the word out, and that this is a common thing that is brought up in our discussions, as well as teaching others and sharing more of that. I think it would be fantastic to try to hook into the contractors but I think that's really hard. I think generally contractors, following rules is somewhat of not their best core competency. So, I think there's like a lot more opportunities to be effective. And I think advertising some of these programs for homeowners, this has been awesome to get the word out. And I know like we're socializing, we're working with Dirk, our systems going in, but I mean, I'll be honest, I bought it and I still am like interested to learn more about how it works. So I guess to answer the question directly, I do think there is some efforts going on to do this more. I think with IRA, people are finding out that there's money on the table to make some of these improvements. And, it is part of the going forward plan for humanity. So, I did have a separate question though, unless others want to weigh in on the topic of information sharing. Thank you, Mac. This has been so cool to learn. So I just wanted to go back to Jim's question a little bit. And this is something that we found hard when we were looking into different options for our project in the park. Marcia, if you wouldn't mind muting, thank you. So when you mentioned that there are heat pumps for every temperature, my head just goes to, you know, climate change. We're having more of these -50s. And it sounds like the problem is solved, but I would love to understand how it's solved with a little more confidence around some of these extremes. Because when I think about setting myself up for adaptation, how am I preparing my home for these like increasing extremes? And what are my boundaries? What do I need to do if I'm going to run into a problem? And that's kind of like on the sell to my friends of like, how do I answer that question adequately?
So could you give me an example of what that really means?
Yeah, so do I need to ask my heat pump installer to install a certain kind if I want to be prepared for -50? Or do I ask for the regular heat pump and I'm fine with -5? And I just go to a friend's house when it gets to -50? Like, what do I do for my kids?
No. So I didn't mention, no, said on my heat pump, I forgot to mention, and on the top of that fan, I have a 6 kilowatt heater, resistance heater, electric resistance. So it is provided as a backup, not as supplemental heat, but as backup. And again, I'm not sure I'm answering your question. You don't have to, I think if there's one takeaway I tried to get that very last slide was that you have to know what's the load you have for your particular house. How much energy do you need? So what a load calculation does, so what any heating or cooling system does, it has to provide the amount of energy equal to the amount of energy you lose. So in the heat calculation, it'll tell you, say, if you say, I want my house to be at 70 whatever degrees when the temperature outside is whatever. So given those two parameters, the installer will provide you with a heat pump that will meet those conditions. Okay, so but when in the old days people say, well, my heat pump didn't whatever, is that, well, it wasn't designed, you didn't choose a heat pump that matched your needs. I don't know, am I making sense? If you know what your heat load is, then the installer should provide you with a heat pump that will meet those requirements. And so,
Well,
now if say you want to be able to have a heat pump that will provide you 100% at its rated coefficient of performance at say minus whatever, then you get a heat pump that would do that. But let's say you'd have that same problem with a gas-fired furnace. It's size for whatever your heat load is. So there's really no difference. The difference is that a heat pump does have the coefficient of performance does change with the temperature, but not, and at some, but it will provide the amount of heat and cooling that it was designed to provide. But once you get outside that range, just as with a gas furnace, if indeed we have a temperature that's minus 30, then we're all out of luck. So in my case, I would have a resistance heater that would provide some heat, but it's just gonna keep the pipes from freezing, but it's not gonna provide my house with anywhere near what the load is. So does that make sense? So I think you can't worry about those extremes. So
Can I ask how your house did in those? And we've had some instances over the last couple of years where it's been 30, a high of -25 and maybe -35 at night. We've had some of those in the last couple of years. So can we just ask how your house responded? What it was like in your house? Because you're a great example of those rare occasions.
it was fine. I didn't even use the backup at all. So,
Plus, it takes
If I'm not
time.
pardon?
If I'm
I
not
was just gonna
mistaken, the record cold for Chicago is 27 below. I remember being in it and hardly anybody's car would start. And I don't think you can go out and buy a heat pump routinely without going out of your way that would handle 27 below. I think you'd have to have a little supplementary something. I'm sure they can be designed, but are they available? You can't get them off the shelf, I don't think.
Yeah.
That's why
yeah.
government is putting an incentive to win a prize by making one that's good to 15 below.
Yeah.
It depends on how long the low temperature lasts. Your dwelling itself is a heat sink that radiates heat after, all through the night. Our cold, ultra cold days have generally lasted a day or two.
Yeah.
So, yeah.
So again, basically, I'm not sure that I really, but Ken is really getting at the real point, So designers try to provide a system that will provide you the full load of your house down to some temperature that's the most probable lowest temperature you will see. When you have an extreme outside, for example, if in the Chicago area, we said that you will get a temperature of minus whatever, the lowest temperature, average temperature you will receive is whatever. So systems are designed to deliver a full capacity at that temperature. When you get much below that, then you either gotta have some sort of supplemental or whatever, or as Ken pointed out, how long is that typically gonna last? Will it be hours? Or it's unlikely that it's gonna be weeks or months. So if that happens, then we're all in trouble, regardless of what kind of heating system you have. Does that make sense?
I think it just helps to feel more confident about it. So thank you.
Yeah.
So, Mac, can you clarify? When we get below the design temperature of the heat pump, it still is producing heat, just not as much as it was designed to do?
Yeah.
Is that correct?
Yeah. So, for example, if you have an air source heat pump that has a coefficient of performance of 3, say, and you want it to deliver its full load at a coefficient of performance of say no less than 2.5. Once you get outside of that range, it will begin to drop. It will still be producing heat. But if the temperature gets so low that it drops, becomes 1, then it's not a heat pump anymore. So to answer your question, yes, it'll still be producing heat, but the coefficient of performance drops. Yeah. So with the modern heat pumps with VFR system, that line where it stays, the coefficient of performance stays almost a straight line And then at some rather extreme, it begins to taper off. So that makes sense.
Yeah, it sounds like it works out just fine. It's not running like it does when it's better temperatures, but it's not going to be it's not a blocker to installing the system.
Right.
Now, Marcy posted on the chat the link to a list of installers. I don't know who's seen it, and I don't know if there's a way to download or keep that list of installers. I mean, that link, it's a complicated looking link.
So I think people should take advantage of not just talk to people over the phone first. Ask them if they will do a heat load calculation or who would do it for you. Ask them, they have a certification. For example, I talked to the guy on, I forget his name. He installed trained Mitsubishi system. He has an office on Chicago Avenue. So he's been certified by Mitsubishi, I guess it is. So there's certification. So you can get heat pump kits. Like there's a guy, a fireman in Oak Park who installed his own system. And so you can, like that first thing I showed you, that was actually a kit. You saw the guy opening the box. So they provide all of the information that you could. So in that system, you just hang the mini split on a wall. You drill a 3-inch hole through the wall someplace. You run the tubing. The tubing is already charged with refrigerant. The indoor and outdoor coils are charged with refrigerant. You connect them together and they send you a little thing to check for leaks, and you open the valves and that's it. So, but in a more a full house system, you want somebody who has the training.